Hey everyone, and welcome. Today, we are diving deep into what might just be the secret ingredient in machine learning, feature engineering. It's one of those things that can totally make or break your model, and we're about to find out exactly why.
Right out of the gate, our source makes a pretty bold claim. It says that how you prepare your data can actually boost performance more than the fancy algorithm you choose. Just let that sink in for a second. The prep work can be more important than the final tool you use.
It's a huge statement, isn't it? So, what does it really mean to engineer a feature? How do you take all this messy, real-world data and turn it into something a machine can actually understand and learn from? Well, that's exactly what we're going to break down right now.
Okay, so first things first, we have to get one thing straight. Machine learning models, they just can't work with data as it exists in the real world. They basically speak their own language, a language of numbers, and it's our job to be the translator. You know, a great way to think about this is the culinary concept of mise en place. It literally means everything in its place. No chef would ever just toss a whole onion and an unpeeled carrot into a pan, right? Of course not. They chop, they prep, they get everything organized first. Feature engineering, that's our mise en place. It's all the essential prep work we do before the cooking even begins. Just take a look at this raw data. We've got numbers, sure, like age and income, but then we have text, like hi or north. A model has zero idea what north means. And just look at the difference in the numbers. An income of 55,000 is going to look way more important to a model than an age of 45, just because the number itself is so much bigger. This is the problem we've got to solve. So our first job is pretty clear. We've got to translate all that text into numbers that a model can actually work with. Let's dig into how that's done. The source material points out that text data really comes in two main flavors. First, you've got nominal data. This is stuff where the categories don't have any kind of natural order. North isn't better or worse than south, they're just different. Then you've got ordinal data, and this stuff does have a meaningful order. High status is definitely greater than med, which is greater than low. Spotting this difference is absolutely key. And since they're different, they need different solutions. For that nominal data, the regions, we use something called one-hot encoding. This basically creates a new yes-no column for each region. Is it north? 1 for yes, 0 for no. Simple. But for the ordinal data, we use ordinal encoding, which is much smarter. It maps low, med, and high to numbers like 0, 1, and 2, which keeps that super important ranking intact. So let's be super clear on this. With ordinal encoding, we're not just swapping words for numbers randomly. We're creating numbers that carry the exact same meaning, the same ranking, as the original text. The model now gets it. It understands that a 2 is more than a 1, just like high is more than med. All right, so we've dealt with the text. But what about that other big problem we saw? The crazy difference in scale between our numbers? Let's go ahead and tackle that right now. Exactly. I mean, if you're a computer and you don't have any context, which number looks bigger? It's not a trick question. The model is going to give way too much importance to income just because 60,000 is a much larger number than 40. This can completely throw off the learning process, making the model think income is thousands of times more important than age, and that might not be true at all. And the fix for this is a fantastic tool called Standard Scaler. What it does, essentially, is it squishes and stretches all of our numerical features so they're all playing in the same sandbox, centered around 0 with a similar range. By putting age and income on the same scale, we make sure that neither one gets to bully the other just because its numbers were bigger to begin with. It completely levels the playing field. So now we have the tools for the job, right? We know how to handle text, we know how to handle numbers, but just applying them one by one is messy, and honestly, you're just asking for trouble. So how do the pros put it all together in a clean, repeatable process? Well, that's where the blueprint comes in. And this is so important. You have to be super systematic to avoid really common but really bad mistakes. And maybe the worst of them all is something called data leakage. It's basically when information from the data you're supposed to be testing on accidentally leaks into your training process. It's like letting your model peek at the answer key before the test, and it gives you a totally fake sense of confidence. And this is the professional workflow that prevents all those problems. First, you just sort your columns into groups. Then you use this brilliant thing called a column transformer, which basically acts like a traffic cop. It directs the numeric columns to the standard scaler, the ordinal columns to the ordinal encoder, and so on. Finally, you bundle that whole preprocessor up with your actual model into one neat package called a pipeline. And that's the magic trick. The pipeline guarantees that all the prep work is learned only from the training data, completely preventing any data leakage.
Now here's a little pro tip, pulled straight from the code. When you're using one-hot encoding, you'll see this little option, drop equals first. Why is that there? Well, if you have, say, 4 regions, this tells the encoder to only create 3 new columns instead of 4. Why? Because that 4th region is already implied. If the other 3 columns are all 0, it has to be the 4th one. This avoids a problem called multicollinearity, which is just a fancy term for giving your model redundant information. It's a tiny detail that makes a big difference in building a solid model.
So, after all that work, the translating, the scaling, building that clean, leak-proof pipeline, what do we get? A final test accuracy of 82%. And that's the payoff, right there. That number isn't just a score, it's proof. It's the validation that being systematic and thoughtful about how you prepare your data is what actually gets you a reliable, high-performing model in the end.
But here's the final question. Do you really need to do all of this every single time? Knowing when these techniques are non-negotiable and when you can maybe skip a step is the last crucial piece of this whole puzzle.
And this table right here is your practical cheat sheet. This is one of the biggest takeaways. So notice, every model needs text encoded into numbers. That's a given. But scaling, that's a different story. Tree-based models, like a random forest, they don't really care about scale. They just make decisions based on splits, like, is income over 50K? But for any model that relies on distance, like k-nearest neighbors, or gradients, like logistic regression, scaling is absolutely 100% crucial. Without it, the huge numbers from income would completely overwhelm the calculations, and age would become almost invisible. So let's just wrap it all up. The message here is simple and it's powerful. Taking the time to really understand your data, to translate it, to scale it properly, that's not just some extra step you do if you have time. It is the absolute foundation that great machine learning models are built on. So remember, the real power isn't just in the algorithm. It's in the quality of the data you feed it. And now that you know how to do that like a pro, you're not just building models anymore. You're becoming a data translator, ready to find those patterns that everyone